Hi everyone, great you're back for today's software bootcamp. We have an exciting day today with Terra Quantum and QMware, our sponsor and great partner that we have been working with since last year and really grateful for the wonderful collaboration. Today we will have a spotlight of Terra Quantum first, where Kim will introduce the company and what kind of careers there are at the company. And very special, one of the Terra Quantum employees is there who was in the WOMANIUM quantum program last year and started her job at Terra Quantum through the program. Then, after 50 minutes, the software bootcamp by QMware and Terra Quantum will start to solve the traveling salesman problem with QUBO formulation, led by Margarita VESHCHEZEROVA and MARKUS BUCHBERGER. And there we have awards as well, prizes. 10 people who have been doing well on Canvas and are willing to host a mentor session will get access to the QMware platform, where they can go through all these exercises and other challenges and then host a mentoring session on it to enable many more people to enjoy this. More about that soon. Now, I will give the stage to Kim for an introduction to Terra Quantum.
Awesome. Thanks, Marlu. All right, so welcome to WOMANIUM 2023. My name is Kim Xu, and I'm head of product management and product marketing at Terra Quantum. We are really thrilled to be a gold sponsor this year for WOMANIUM. And in case you haven't heard of us, we are a leading European deep tech startup located in St. Gallen, Switzerland, but we are a global company. So we've got people all across the globe. I am actually located near Washington, DC. And in a few minutes, you're going to hear from some of my colleagues who are located across the globe in Europe as well. We are the world's elite business performance enhancement company, and we specialize in hybrid quantum computing. Now, you may be wondering, what is hybrid quantum computing? We combine classical and quantum computing technology to solve real-world problems across a variety of industries. With us, organizations can innovate faster, increase profitability, and become more efficient. So we have 15 minutes at the beginning here for the spotlight talk. I'm going to give you some background on Terra Quantum, and then I'll invite some of my colleagues to talk about our diversity of careers. And then shortly thereafter, like Marlu just mentioned, we will be working on the traveling salesman problem with QUBO with QMware. So let's start with a little bit about us. Terra Quantum was founded in 2019, and we've raised over $90 million to date. We are led by a distinguished and highly decorated management team with deep expertise in quantum physics. And our team is comprised of international experts from science, academia, and industry. We have one of the largest R&D teams in the global quantum space with over 150 quantum scientists, and we're one of a few companies globally to take quantum technology from science to commercial application. So we deliver end-to-end capabilities in 3 primary areas, and I'll talk about each in turn. The first is quantum algorithm design. The second is quantum computing, and the third is quantum security. So let's look at algorithms first. We specialize in building algorithmic solutions for a wide range of optimization, machine learning, and simulation problems to save our clients millions of euros in industries like aerospace, financial services, automotive, chemicals, utilities, and healthcare. Whether it's reducing empty miles, optimizing collateral portfolio, better utilizing solar cells to improve energy supply, reducing CO2 in biomass power plants, or a host of other applications, we love partnering with our clients to find solutions that weren't possible until now. It is really, really thrilling to work with clients on the cutting edge of technology. And I just have to say, for me personally, this is a passion area, and I think it's just one of the most fascinating times to be alive. So I feel really privileged to work in this space. And it's only getting better. So our technology has the potential to improve energy efficiencies through optimal grid management. We can accelerate drug discovery processes and improve prediction and simulation of complex systems like weather patterns. But the software is only as good as the compute power. So next, let's look at our quantum computing products. So we use our proprietary and patented hybrid quantum cloud in partnership with QMware, which you're going to hear about in just a few minutes. And through that, customers can develop and test quantum algorithms in classical environments on emulated and simulated qubits before deploying them on native quantum processors. And the reason that's important is because it saves time and money, because quantum computers are still expensive. Also, some solutions can actually run quite effectively on classical computers. So we try and take advantage of that as much as possible. Our goal is to maximize available compute power while minimizing the computing costs for our customers to find the best solutions. So our third product suite is security. And you may have heard our exciting recent announcement, but if you haven't, I'm going to tell you all about it. So we recently set a world record for the transmission of quantum encrypted data, paving the way for unbreakable global encryption over existing fiber optic networks. We transmitted data encrypted with quantum keys over a 1,032 kilometer fiber optic network at a speed 10,000 times faster than the previous record, breaking both the speed and the distance records. And you can read more about this major achievement in Nature. Now, why does that matter? When quantum computers become mainstream, the encryption that secures our most sensitive files and communications today will become easily crackable. That might seem futuristic, but the truth is it's very relevant now due to the store now, decrypt later risk, which is the threat of a malicious party stealing encrypted data today, which they can't yet crack, and then waiting until quantum hardware matures to decrypt the data in the future. So it should come as no surprise that securing data and making transmissions tap-proof now and in the future is of interest to a number of government institutions and companies, and this is where we can help. We offer an end-to-end quantum security upgrade. Our offerings form a comprehensive and secure approach to quantum security with three main elements. The first is a novel quantum key distribution, or QKD protocol, that provides quantum encryption over world record-breaking distances, like we just talked about. We have our quantum random number generators, which meets NIST standards and are approved by METAS. And we have a post-quantum algorithm library. So those three things together comprise our quantum security package, and we would love to talk to you more about that if you're interested. There's a lot happening in the security space, so if you haven't started looking into it, now is the time so that you don't delay. So that is it. That's my overview of Terra Quantum and our products and why we are super excited about the future. And now I'd love to talk more about careers. So I'm going to introduce you to some of my colleagues who are going to tell you a bit about their roles at the company so that we can see a cross-section of what different roles and responsibilities look like. First, you'll hear from, first you're going to hear from Sidney Nye from our commercial team. She came to us through the WOMANIUM program last year. You'll hear from Asel from Applied Research, and you'll also hear from Nheela from our product and brand marketing team. So with that, I'll turn it over to Sidney Nye.
Thank you, Kim. And yeah, hello everyone, I'm Sidney Nye, and last year I had a great opportunity to participate in the WOMANIUM program while completing my master's in applied technology. I was relatively new to the field of quantum computing at the time, and the WOMANIUM program provided an excellent launching pad for me in that space. So currently I hold the position of Quantum Venture Builder at Terra Quantum, where I lead our initiatives in the manufacturing and logistics industries. So this role perfectly aligns with my academic and professional background, allowing me to blend knowledge of business and technology. On one hand, I delve deep into our research and development to gain a comprehensive understanding of the latest advancements. This helps to identify the problems that can be effectively addressed using our technology. On the other hand, I cultivate extensive industry insights to uncover the most pressing challenges and issues that need attention. So every day brings new challenges and exciting opportunities. And yeah, every day of my work is pretty much unique. Another aspect of my role that I find particularly rewarding is collaboration across the organization to deliver the best performing solutions. I work closely with teams ranging from R&D, applied research, to product marketing and engineering. And maybe last but not least, remarkable aspect of our organization is its diversity. Working with individuals from various cultures and backgrounds is an experience that I personally appreciate a lot. I think that sums up my perspective. And now over to you, Nheela.
Thanks, Eti. Hi, everyone. My name is Nheela. I am based in London, and I have the privilege of managing product and brand marketing at Terra Quantum. I'm also very much delighted to be here today. So as a product and brand marketer at a deep tech, cutting edge company, my position is a fascinating mix of understanding the market and then aligning this with the ever-evolving capabilities that we have at Terra Quantum and shaping our products for products positioning for optimal impact. For me, just as Kim said as well, it's a personally very exciting position to be in because I've been personally interested in the industry for quite a few years now. It's beyond exciting and motivating for me to know that we are leveraging nature's inherent properties in enhancing our practical reality today. It's something that I have to keep reminding myself that this is actually happening, and it's really a privileged place to be in. And to give you an insight into my role, there are many sides to it, but it starts with understanding the pain points of the market, and particularly from my side, the perception barriers that businesses have that prevent them from tapping into the potential of hybrid quantum tech. So this involves interacting with the industry, be it via events or direct conversations, and also collaborating closely with our applied research team that we have Asel here today, and Seti as well, to comprehend the vastness of the capabilities that we have, which is not a small task given the vastness of how many different aspects we're tapping into. And then equipped with this knowledge, my task is to package our products in the most optimal way, so that the offering that we have aligns with marketing demands. And another part of my role is also bringing these products to market. And so this entails creating marketing strategies and reaching out to our target audience in order to generate awareness about the disruptive potential of quantum tech and our specific products. And yeah, overall, this position of witnessing firsthand the progress of scientific development and its real world impact is truly awe-inspiring. And yeah, to wrap it up, I would say that this position enables me to not only create a bridge between the products that we have and the needs of the people that can use them, but also for me personally to bridge what I enjoy doing with the value that I can provide. So yeah, with this, I'm going to turn it over to Asel.
Yeah, thank you, Mihaela. Hello, everyone. My name is Asel. I'm quantum machine learning researcher at Terra Quantum, and I'm thrilled to have this chance to speak to you about my work in the exciting field of quantum technology at WOMANIUM's remote conference today. As a quantum machine learning expert, my background spans the fascinating fields of quantum physics and quantum cryptography, but today I work primarily in the exciting realm of quantum machine learning. My role at Terra Quantum is centered around solving problems for our clients, and we work to build new solutions or improve existing ones using the power of quantum machine learning. A key focus is hybrid quantum neural networks, which combines the best of quantum and classical computing. But there is more to my job than just problem solving. As my team and I delve into these challenges, we often find ourselves inventing brand new models, and our discoveries lead to writing scientific articles that get published in very good scientific journals. What is really exciting is seeing our work directly benefit the industries we serve. It's like seeing our ideas come to life and make a difference. This is unique satisfaction that comes with the immediate application of our findings. To see our inventions can solve real-world challenges, enhancing customer solutions today is exciting. And I also work on creating patterns in quantum machine learning, and this forms the basis of our library. We're building all about various hybrid quantum layers, hybrid quantum neural networks, and the goal is to make creating hybrid quantum models easier and more automated. Sure, there is a lot to do, and it's not always easy, but the work is incredibly exciting, and every day presents a new puzzle to solve or a new discovery waiting to be made. And I am fortunate to love what I do, and even more thrilled to share my passion with you today. And thank you for your time, and we are looking forward to your thoughts and questions. Thank you.
Thank you. And there are many questions. The first one is for Sidney Nye. How have you prepared yourself for industry?
So I'm probably, let's say my background is probably different from most of the people, most of the participants. That's what I found very challenging last year, that I'm not coming from scientific or engineering background, but I did study applied technology. I also have professional experience in the industry. So this is where my industry insights are coming from. And my education, including my participation in WOMANIUM program, was to expand my horizon and learn more about the technology and quantum computing. Yeah.
Could you share also a bit broader, Kim, what kind of people is Terra Quantum looking for? What are skills that are needed? What are requirements?
Yeah, that's a great question. So across the board, I think we're looking for all different types of skill sets, definitely in the applied research space and quantum physicists, of course, as always, but also definitely in the industry space. So for example, the product team, as we start to scale our operations and our products that we're bringing to market, we're going to need different types of skill sets that don't necessarily have expertise in a quantum background, but that do have expertise in other areas like commercial and product and UI, UX and things like that. So lots of opportunities. Keep an eye on our website.
2 questions for you, Asel. Is it possible to share an example of one work with us that you have done for a client? I know that maybe this is not possible.
Yeah, sure. We have big project with Thales. Yeah, it's a very big company, and we create a solution, hybrid quantum reinforcement learning for satellite mission planning. Yeah, and you can find more details in our scientific articles on arXiv now, and they've been reviewed now.
Then from Rajat, how to start with QML with a physics background, Asel?
Yeah, quantum machine learning is a combination of quantum computing and classical neural network, classical machine learning at all. And yeah, just know quantum physics. And if you're a good classical programmer, I think, yeah, you just need to believe yourself and yeah, practice more.
Nheela, what is your daily work life like working at Terra Quantum?
There is a great variety from day to day, but I would say it's a mix of having this interaction with the community that we're addressing in terms of generating awareness and talking about our products. So there is the interaction with the audience, and then there is the kind of the background part of understanding. Let's say we have a new product that has been packaged by the applied research team. It takes understanding the product and looking at the best ways to position it, to create product materials like brochures and ways of kind of educating the public and breaking all of these concepts down in the easiest forms. So yeah, I would say that that is probably the bigger highlights.
Fantastic. Then a last question, and please, Kim, guide to the right people. Can you share more about what typical roles physicists have at Terra Quantum, computer scientists, others?
Yeah, sure. So I think maybe the best way to talk about it is just look at the folks who presented today. This is a great cross-section of the organization. And in a minute, you're going to hear from Margarita and Markus, and they'll talk you through the traveling salesman problem as an example. This is a really great representation of the breadth of roles that we have. So yeah, if you're a quantum physicist, you're probably doing a lot of R&D. If you are a developer, you're probably actively working on some of our digital products to get them to market. If you're in product, you're doing some of the things that Nheela was just mentioning. If you are in the commercial team, you're working on some of the things that Sidney Nye mentioned earlier, where we're working on figuring out how to bring them to market. So that's probably the best representation. I would say just think about it with that breadth.
Excellent. Thank you so much for this fire and Q&A. We will have Terra Quantum again at the career fair, and now 3 hours of bootcamp together with QMware. very excited for that. Asel, Satanai, Nheela, Kim, thank you very much. And I will now give the word to Vardan, my team member, to introduce the software bootcamp with Marcus and Margarita.
Hello, everyone. Welcome back to the Software Bootcamp. And this week we are having one from Terra Quantum and QMware. We have two extremely fantastic speakers with us, Marcus and Margarita. They are both experts on the quantum algorithm side, and they would be following a lecture, a specific software bootcamp on how to solve the traveling salesman problem and define QUBO formulations. So over to you both. Please take it away.
Yes, thank you. Hi, my name is Markus BUCHBERGER. Hopefully you can hear me.
Yes.
Okay. So my background actually is computer science. I'm from Germany, Munich, and I studied computer science in the early 90s. And I started quantum computing like 4 years ago. And yeah, today I'm working at QMware, and I'm responsible there for some SDK development and also for the training and education part. And as my background is not a physics background, just a computer science background, that's why I have also Margarita with me. She can help me with that. Over to you, Margarita.
Yeah, okay. Hello, everyone. I'm really happy to be here today with you. So my name is Margarita, as you might have understood by now, and I'm a senior optimization researcher in optimization. I'm senior optimization researcher at Terra Quantum. So I started 6 months ago, and before this, I was doing a PhD in quantum computing applied for optimization problems. So my background is a lot about computer science mixed with physics and with a very specific point on quantum computing. So I didn't do something really far from what I was supposed to do in my life. And now at Terra Quantum, I continue to work on optimization problems. I try to design hybrid approaches for them. So by combining the best of the classical and the quantum. And I'm working both on client projects, like the one that was mentioned before, and also on internal projects where we try to push further the research. Okay.
Thanks. Yeah, then let's take the best of the 3 hours that we have, and I will start now, and we go into the real stuff. Maybe just one more annotation. So QMware and Terra Quantum are sister companies. So we have a very strongly coupled relationship and collaboration. And that's why we're also doing this workshop here for both companies with speakers from both companies. I will very shortly tell a little bit about QMware and about the product that we have, and then we'll dive into the technical stuff. So I just fight a little bit with the Zoom app. It hides some controls. Okay, here we are. Okay, so what is QMware offering? We offer a quantum compute as a service through our hybrid quantum cloud, which we will see later, and which also some of you will get access to it after the workshop. So quantum compute as a service is one of our main pillars. Also quantum safety as a service. There we, together with Terra Quantum, we investigate and build solutions for quantum key distributions, quantum random number generators, and so on. And also quantum algorithms as a service as well, here in a very tight collaboration with Terra Quantum, where we analyze real world use cases, business cases from companies, and try to find an advantage by using quantum technologies. In our opinion, for the time being and also for the next years, the quantum computers will not scale the number of qubits in a regime of billions or billions of qubits. So that's why we believe that for the time being, it's the best approach to have hybrid quantum computing, where we mix quantum technologies with existing classical compute paradigms. And as you can see here on the right side, you see existing hardware and software. I mean, we have a lot of specialization also in the classical work. Beside a regular CPU, there are GPUs, there are TPUs, there are all kind of specialized processing units. And now, with the power of quantum technologies, we get another specialized processing unit, which is a quantum processing unit. And we are providing access to those kind of quantum processing units. They could either be simulators, so classical computers which simulate the behavior of a QPU, or access to native QPUs. On top of the hardware, of course, we need complete new kind of software stacks. So we are offering hardware abstraction layer where you can access different kind of QPU vendors, simulated or native. And on top of that, we need a new kind of building blocks to build applications. And Terra Quantum is here developing a lot of libraries and knowledge and experience in the area of optimization, machine learning, cryptography, or simulation.
Okay, so yeah, so just let me come back a little bit to what was discussed by Kim already. So what are the kind of application and this kind of softwares that we offer in Terra Quantum, and like maybe it is also accessible through QMware? It's basically 3 different applications that you can handle with quantum or hybrid quantum methods. So the first one is the optimization. And by optimization, we mean such problems like the scheduling problems, the resource allocation problem, the routing problems, and so on, that are very important for the industry today. And so what we managed to do with quantum methods is actually to outperform the existing classical solvers on some problems in terms of a quality of the solution for a similar runtime. So that what concerns optimization. So then for machine learning part, we also aim to do better by combining the strengths of classical and quantum computing. So for instance, by using what we call the hybrid quantum neural networks. And basically we're aiming to hit on two metrics which are super important for the machine learning: the prediction accuracy and the generalization of the model. And as you can see, maybe on the plot downstairs on the bottom of the block, is that with hybrid we are actually able to do much better in less by using a shorter training time. So then we also attack the simulation, and here we do something which is kind of a little bit original and different from what I've just mentioned, is that like between this quantum and hybrid quantum, there is another kind of algorithms which are like sometimes mentioned together with when people talk about quantum computing, and these are quantum inspired algorithms. And by quantum inspired algorithms, we mean we understand all the methods that came out of the physics, which were developed for physics application and which we can now leverage for computing tasks. And for instance, what we have done is that we have improved the running time. So we had significantly decreased the running time for the simulation of a system whose dynamics obeys a partial differential equation, by using this like methods which are quantum inspired and which come out of quantum physics.
Thank you. Yeah, as I said, QMware is providing a quantum cloud. It's a private hybrid quantum cloud. You need to register and you need to get in touch with us to sign a framework contract or something similar. And from there on, you can have access to our QREs, quantum runtime environments. Basically, these are Docker containers installed with different kind of hardware resources like memory, CPU or GPU, compute power, access to QPUs, and so on. And we will see in some minutes how the access to this hybrid quantum cloud will work. Basically, you just need a browser, so then you can access the cloud. And from there on, you can work, for example, with our Jupyter server or with via SSH access to develop applications on our systems. So why could QMware special? We combine quantum power, hybrid quantum computing with high performance computing. So QMware has also a strong relationship to one high performance computing builder, constructor, who delivers systems into data centers. And so we provide, we have a very long experience in building up data centers and providing their high performance computing systems. And now we combine these high performance computing systems with quantum technologies to build hybrid quantum computer systems, which are really, really fast and where we can try to tackle real world problems and to solve them better with quantum enriched approaches than the best classical solutions at the moment can do. We have an end-to-end stack for hybrid quantum algorithm development. At the moment, our nodes from last year, they provide 12 terabyte of classical RAM per node, which allows us to simulate up to 40 qubits. We could cluster these kind of nodes together, so we could also go up to 41, 42 simulated qubits. This is for the moment a big advantage because there are not so many physical QPUs existing which can really provide 30 or 40 qubits which have a good error quality and a good coherence times and so on. But of course, this is just hopefully a temporary advantage because of course we all expect that quantum computers will scale much higher in the next years. We have on top of the quantum hardware where we provide virtual quantum processing units or native quantum processing units, we have some hardware abstraction layer, and on top of it, we are providing APIs to access our systems, and we are also providing an SDK with a quantum programming language, we call it BASIC, which allows us to, or allows the developers to build circuit-based quantum algorithms with programming languages like C++ or Python. So this was a short introduction about the services that we have. If there are no questions, and I would expect no questions here yet, I would like to introduce you to Cognite. Cognite is the name of our cloud. You need to have a contract and you need to have the right credentials to enter the cloud. And as soon as you enter the cloud, it's quite easy. You would see all the quantum runtime environments that you have access to with the credentials you logged in. It could be only one, or it could be multiple queries. That depends on what you ordered or what you are paying for. And from there on, you can click one of the links to jump into a Jupyter server, where you will find in the standard installation, you will find a number of prepared tutorials, documentation, tips and tricks. Even so, if you are a starter in quantum computing, or if you are advanced, like probably the attendees today are, you will find here, I think, interesting stuff to learn more or to try out things, how certain topics work on our platform. Especially if you're a starter, I would recommend the Welcome notebook, where you see like a hello world, how to build your first small quantum algorithm. And of course, the basic SDK documentation notebook, which gives you an overview of the SDK that we have of different kind of patterns, methods, how to implement certain things. So on the next slide, I would like to give a very brief overview of the architecture.
Sorry, Marcus, for interrupting. We have a question. We have questions in the chat.
Oh,
so, for
great.
instance, the questions are: can is it the moment to open the laptop and to try to code something, or now it's just the observation part? Like you have just described all this like setup stuff, and people are asking for a Jupyter notebook or whatsoever. So
the plan for today is we will go through some theory at the beginning. I will tell you a little bit about quantum Fourier transformation, quantum phase estimation, and variational quantum eigensolvers. And then we want to implement or to solve the traveling salesman problem based with our platform and our SDK. Because we are short in time, we decided at the end that I will do the exercise live, like implementing the stuff, and you can watch me, and we can let it run and discuss it and answer questions. And for some of you, there will be a trial access for some days or weeks, where you can then try to do it on your own. Would that answer the question? Because I didn't really get it.
yeah, I think that you answered the question. So
Okay, thank you, Rita. So what is our software stack? We have a C++ kernel or a C++ core implementation, where we implement all the core features which we need for building quantum algorithms. We focus a lot on universal quantum algorithms. So we use the universal gate model to build circuits. In these circuits, we can use different kind of operations like Hadamard, X, Y, Z, or rotations, single qubit, 2 qubit, or 3 qubit operations. And all this kind of core functionality is implemented in C++. Why is it C++? Because we want to implement the core functionality very close to the hardware to make most of our power of our high-performance computing systems. On top of the C++ core library, we have a C-based API, which is able to allow us to connect high-level programming languages, for example, Python, or maybe in the future Java or C#. At the moment, we support Python only. And of course, we also have a Quasm import-export API, where you can produce Quasm out of the circuits you build with our system, or where you can import Quasm to construct circuits on the run and let it run on our system. In this C++ core library, we differentiate two areas, which is called the Q userland and the Q kernel. In the Q userland, we implement all functionality which is independent of the underlying backend, of the underlying QPU or simulator capabilities. So this is what is general and what is expressed via our API. And in the Q kernel, we have a hardware abstraction layer. We also have a kernel extension layer where we can implement extensions and we can inject them into the system. For example, to implement different kind of noise models. If we want to emulate specific QPUs to see if an algorithm that we have developed would make correct computations on a specific QPU, we could implement, if we have the specifications of the vendor, we could implement a specific noise model and then emulate this QPU to see if our algorithm would give us good results on that QPU. But we can also use other kind of extensions. We could, for example, we have as a sample, we have a timer extension where you can benchmark all the calls. So in case you are about to analyze performance behaviors, so you could here intercept all calls and see how long does it take to execute certain gates on a certain backend. And very much on the bottom, we have different kind of adapters where we can connect to different simulators or to different QPUs, like for example, Ionic, QEra, Rigetti, or what else. So we have several QPU vendors. We already have contracts and we already prepare the integrations. I think I must not name, or I must not tell you all the names. And also, of course, we have different kind of simulators. We have CPU-based simulators. We have GPU-based simulators. We are also working on tensor network-based simulations and so on. Okay, so this was a short introduction in the cloud, in the software stack. Are there any questions so far?
Nothing in particular, I guess.
Okay, great. Then, Rita, may I give over to you?
Yes. Okay. I think that you're supposed also to have some prior knowledge about quantum computing, so I'm going to keep it short. So let's just review the basic notions. So, for instance, you have already heard about qubits. So qubit is a basic unit of information in quantum computing. For instance, like in a classical computing, you're familiar with the notion of bit that can be in two states, in 0 or 1. So when you go to the quantum, things change dramatically. So for instance, a state of your qubit is actually characterized by two complex numbers. So, and a complex number, so you see this wonderful animation like in different locations. So two complex numbers basically are 4 degrees of freedom. So for instance, you have real imaginary part for the first one, real imaginary part for the second one. So and the reason why you can represent them as a vector on a 3-dimensional sphere, the so-called block sphere, is that actually there is 1 degree of freedom that you don't really care about, because like there is a correspondence between these complex numbers and the solution, so the so-called measurement solution. And their measurement is the only information that you can get out of the qubit. So a qubit is a physical system which is quantum. You are classical, so you can you can see only the information which is a classical information. So what kind of classical information we can get out of a qubit? So out of the qubit we get something which is called the measurement result. So measurement result is just a binary number. It's a 0 or 1. And what is particular about the quantum state out of which you get this measurement output is that actually there is a probability to get the output 0 and there is a probability to get the output 1. And these ones depend on these complex values that characterizes the state of your qubit. So and indeed, it imposes one very important constraint on the state of your qubit. It basically is that it should correspond to a valid probability distribution, in the sense that the sum of models of two complex numbers involved in it should be equal to 1. So, and then there is also one other one other particularity is that the probability to get 0 or the probability to get 1 are actually not proportional to the complex number itself, but to the model square of the complex number. So it means if you multiply both complex numbers by the same complex number of a modulus 1, the so-called phase, global phase, like the result of it doesn't affect in any way the result of your measurement. So it means that you actually don't care about it, so you can remove one of the degrees of freedom, and that's how you get this like nice block sphere representation of your qubit. So is there any questions? Yeah, I don't think that there is any question about this, so let's move forward. So now something like the interesting stuff starts to happen not when you have just only one qubit, but when you when you have more than one qubit. So for instance, when you get 2 qubits, like this pair of qubit can be in the so-called superposition of 4 different states: 0, 0 for the first, 0, 1 for like in 1, 0 and 1, 1. And basically the state of the system of 2 qubits is going to be described by 4 coefficients, by 4 different complex numbers. And like it turns out that this vector of 4 numbers can't be always rewritten as a tensor product of 2 vectors with 2 elements. So it means that you can't look at your quantum state of 2 qubits and just say that it's the same that 2 individual states of 2 individual qubits. So this is a basic like mathematical way to check it is to try this vector that you have on the slide, the 1 divided by the square root of 2, 0, 0, 1 divided by the square root of 2, and try to write it down as a tensor product of 2 vectors. And you're going to end up with a conflict of requirements, and that basically means that okay, it's not possible. So you have to deal with that. But this is something which is exciting about quantum computing. So it means that when you get more and more qubits, you get something which can't be accessed, like you get a system which can be just understand as a concatenation of individual qubits. And that's how you get, like, that's where the power of your quantum computer is hidden. So for instance, you have, like, I guess you're also familiar with circuit notation. So in a circuit notation, you basically use a wire to represent each qubit. And when you apply some unitaries on these qubits, they are marked as other rectangles or some special notations. And so, for instance, you can see on the slide the circuit, which can be used to get an entangled state that you see on the slide. Okay, so now I will show you something which is like a small quantum routine, which is called the phase kickback trick. And this phase kickback trick is something which is going to be useful for you which is going to be useful for you later during the tutorial, and which also have some like philosophical value hidden behind it, which is quite interesting. Is that actually sometimes you can have 2 qubits which are in the state that can be that is separable. So for instance, 2 qubits are not entangled with each other, so you can write them down as like 2 individual qubits. So then you apply, like, I guess you're familiar with the control something notation. So you can apply a transformation which is controlled by the first qubit and which affects the second qubit. And you're going to also end up by a quantum state of 2 disentangled independent qubits, but then like this application of the controlled gate going to actually affect the state of the first qubit rather than the second qubit, even if the first one was the controlled qubit, and it means that like it was used to control if the operation happens or not. So if you are familiar with the circuit notation, you can like see that we start with 2 qubits in 0 state, then we put the second in the 1 state, then we apply the Hadamard gate, and then we apply this control NOT gate. So for instance, at the beginning of the control NOT gate, we have the plus state on the top and the minus state of the bottom. And then we end up by having 2 qubits, and the top one is in the minus state and the bottom one is in the minus state. So that's an interesting observation. Okay, so now usually when you program a quantum computer, what you do is that you use this circuit notation. So you declare something which is called circuit, which acts on some set of qubits, and then you can say that, okay, I'm going to add to my circuit a elementary operation. So basically you have, even if like any unitary transformation is a valid transformation for a quantum state, basically you do not like think about every possible unitaries, but instead you take like elementary simple unitaries like the Hadamard, the X gate, the rotation X gate, and so on, and you apply them to a subset of qubits in your quantum register. So for instance, like the application gates that you see here in the interpretation of blocks where put your 0 state in the plus state, the state of the second qubit goes to 1, the state of the, we assume by default that every state is initialized every quantum qubit is initialized in a 0 state. So, and then the third one is rotated around the x-axis. So then what you get in the end, so you get something which is called the state vector. So you get your complex numbers, like here you have 3 qubits. So basically you get 8 2 power 3, 8 complex numbers. Like here, some of them are equal to 0. So that's why you can't see them, in the slide. So then that's how your state vector looks like. And yes, so then what happens, like, and the state vector, typically when you do the computing on a quantum computer is never accessible to you. So state vector is something which exists physically, but you can't get these complex numbers out of it. So but you can have the access to these complex numbers through the simulators. So probably gonna answer the question of people in the chat, so why we care about the simulation. So basically the simulation helps us to better understand how things goes on and what exactly happens to your quantum state, but we are kind of limited with the number of qubits that we can simulate in the end. But then what you can get even with a quantum computer is the output of the measurement, and this correspondence between your quantum state and the probability of getting a specific output actually is translated in different statistic, like in different statistics of different measurement outputs. So for instance, here, like you can observe that the state 0, 1, 0, 0 is has higher probabilities than the state 0, 0, 1, and so on. So yeah, let's move. You can also, like, by using this this circuit notation, prepare a state which is an entangled state. So for instance, when you get this entangled state, like here, the qubit 0 and the qubit 1 are entangled with each other. So it means that you can't show, you can't talk about them as about 2 independent states. So both of them, and you can't, for this reason, you can't visualize them on a block sphere. So and then, like, the interesting thing about entangled states, like especially the fully entangled states, is actually like they are strongly correlated in the sense that when something happens to the first, like when you measure the first qubit, so you accidentally learn the state of the second qubit, and you also collapse your quantum state in a way that corresponds to like the measurement output of the first state, and also like and the second qubit, the second entangled qubit, gets the same value. Like for instance, if you're entangled state, yeah, I guess it's what's happening today. And now one more time, you have 2 qubits, like the first, the second qubit, which were measured. So they are in the trivial state, they are disentangled now. And the third qubit, which is like not affected by the computation because it wasn't entangled with the first 2 ones, and also it wasn't measured, so nothing happened to this guy.
Okay. Thank you, Rita. Thank you for this short summary of hopefully things that you know already and that you are familiar with. Yeah, how could you work with our system? So as soon as you have access to our system and you log in and you are on the Jupyter server, you can create a new Jupyter notebook, for example, by creating a new Python 3 IPY kernel. And this will create a new file, and in this new file, you can then start to do something. You can write content, you can write code, and the code can be executed. And to write code, of course, you need to understand, you need how to use our SDK. Our SDK is called BASIC with a Q at the end. And here you see samples, all the samples are written in Python. So here you see now a lot of samples today, how you use our Python SDK. So first you need to import our package, or basic module is called BASIC. You need to import it, and then, which is a little bit untypical for Python programs or Python modules, you need to initialize it. The method is called bqinit, and this will set up some environments in the background, which are related to our backends that we support. So here, for example, we see a backend which is called QSS QLib kernel. This is a quantum state simulator based on a CPU, and as it runs on a high-performance computing cluster, we see some information about how many NUMA nodes does the system have, how many ranks per node do we have, how many threads per rank, and so on. Here we have a very small configuration, so we only provide one thread, but normally we have like 48 cores or 360 cores available to do fast computations when we do computations on CPUs. We also get some information about the log level, where the log file is located, and we also see the version number of our Python SDK and of our C++ SDK, which normally should be the same version, but different build numbers. So as soon as you have imported and initialized the system, you can start writing code. First of all, you need an engine. An engine is connected with the backend. So an engine can be connected with a simulator or with a real QPU. So in the parameter of the engine, you specify which kind of backend you want to use. For simulators, we support out of the box, for example, QSS DP or SP. DP is a CPU-based simulator which has stores complex numbers in 128 bits, and QSS SP stores complex numbers in single precision, so with only 64 bit, and that makes the difference if you can simulate 39 or 40 qubits. Then we have a GPU-based simulator called CUQS. It's available since last year, and at the moment we provide GPU cards with up to 80 GB of RAM. So that means you can simulate around 31 or up to 32 qubits max. When you have created the engine, the next entity, when you have selected the backend, what you additionally can specify is if you want to load the kernel extension. As I said, a timer extension, which tracks the execution times of gates, or for example, a noise extension, which implements a specific noise model if you want to emulate a specific QPU. Next step would be you have to create a circuit. You instantiate an entity of type QCircuit and you give it a name. The parameter is just a name so that you can identify circuits later. And then you should create registers, for example, qubit registers. A qubit register also gets a name. You have to specify the number of qubits that you want to have in that register, and you can optionally initialize the qubit register with a certain bit string. By default, all qubits are initialized in the 0 state. And if you want to do measurements, you can also, or you need to create also classical registers. Here we create a classical register with 2 bits. And if we let this code run, we would get a state vector, which is in the initial state 1, 0, with a probability of 100%. So here, if we are running on a simulator, we can look into the state vector because it is located in classical RAM, and we can see what state the system is in. The next step would be...
Sorry, Marcus, can you just interrupt you for a sec? So people ask if they can install BASIC with pip install BASIC.
Yes.
Okay, so, and they also ask if there is they can access any documentation for it.
So yet we do not have a free trial version of BASIC. We are working on that. At the moment, it's closed source. We are working on a free release of BASIC. So technically, it's possible to download it, but from an organizational or contractual point, it's not yet public available, but it will come. But it's based on a pip repository. The difficulty is that the basic module, the Python module alone is not enough. We also need the C++ libraries, and we also need, of course, connections to QPUs and simulator backends. This is not that easy to install it on every notebook. That's why at the moment you cannot it's not public available. I'm sorry. If this was the question.
Yeah, I think that was the question. Yeah, so people are urged to try things on their own, so they wanted to install stuff and to run it already, but I guess like now you just observe what is how the things works, and you learn how to program with the library, and then like some of you are going to get access to the QMware, and BASIC is installed on the QMware, so you can you can try it on your own with on the QMware.
Yeah, and stay tuned. We will release a community edition probably of our SDK, which comes with a built-in local simulator where we can simulate maybe up to 30 or 32 qubits, something like that. Okay, the next step would be operate some gates. So you have a circuit object, it's initialized in a certain state, and from there on you can execute gates on the circuit. So here you see a sequence of operations like execute a Hadamard on the first qubit, execute a rotation around pi/4 on the second qubit, and do a CNOT operation between the first and the second qubit. And then if you would execute this, you would get this kind of state vector as a result. And if you would like to look up what kind of operations do we support, there is a Jupyter notebook in the Jupyter server, in the QREs. It's called Basic SDK Documentation, where you find all the operations that we support. Single qubit operations, controlled qubit operations, 2 and 3 qubit operations. So if you want to do measurements, and of course, if you are running on a QPU, you have to do measurements. If you're running on a simulator, you can do measurements. You can also access the state vector, which I will show later. But if you would like to implement an algorithm and run it on a simulator and check if it also would work on a QPU, of course, you would need to do measurements. So you can use different kind of measurements that we provide. We provide measurements at the computational basis for 1 qubit or for qubit registers. For example, here we do a multi-measurement of the qubit register Q into the classical register C. We let the engine run only one time. And then in the classical register, we see the values of this measurement. Of course, as Rita explained before, if we do measurements, we get certain values with a certain probability. So that's why, of course, an execution of one shot normally doesn't make sense. So normally what we do is, if we are running on a QPU, we are executing a circuit multiple times, for example, 1,000 times. And then we cannot access, of course, the classical register because the classical register is overwritten every time. So the engine will track the different results of each shot, and then you can access the result. For example, you can print it, the probability distribution. You can plot the probability distribution in a graphical way, or you can access the result object via the API. Then, if you have implemented something in our SDK, you can, of course, visualize the circuit that you have implemented. You can visualize the circuit in a graphical way, like with ASCII art or with the MATLAB library graphic, where you can see on which qubits, which gates operate, and what kind of measurements you would do. You can also generate Quasm code if you would like to export and run it on a different system. This is a quasi standard for exporting, importing quantum circuits between different kind of quantum vendors. And because we are using C++ as the programming language under the hood, we can also generate a C++ skeleton, because let's say our vision is that Python is a great language for rapid prototyping, for research and development. But if it comes to production-ready solutions, and we want to build production-ready solutions for our customer, we would strongly recommend to re-implement everything in C++. And that's why here you can get, it's a small tool, so you can get a starting point out of a Quasm circuit, for example, and you see what you would need to do in C++ to implement something with our C++ SDK in that case. Okay, the next slide is contains a lot of details, but they are important so that you understand then all the samples that we will discuss in the next 2 hours. So what we have is, we call it the simulation interface. So if an engine object is connected to a simulator, then you have the possibility to call the method simulation to get access to the simulation object. And from there, you can access the state vector. So you can, for example, iterate over the state vector, then you get state vector entries, and you could access each entry. You can get the index of the qubit, you can get the complex amplitude or the probability. Of course, be careful with these kind of operations, because if you are using 10 qubits, you have like 1,000 entries in the state vector. And if you have 20 qubits, you have 1 million. And if you have 30 qubits, you have 1 billion of entries. And then iterating and printing stuff like this would really last a long time and might even crash the system, because the I/O buffer will run over or whatever. So this has to be used carefully. This simulation interface is only accessible if your engine is running in the so-called direct mode. In the direct mode, all operations that we call on a circuit are executed immediately, synchronously. And this is a way to use our SDK so that you can do debugging your application. Because you could somehow step through a quantum circuit, and after each step you can look into the state vector and see how it changed. So either you use our engine in the direct execute mode, where each step in the circuit is done immediately, or you don't use the direct mode, you use the regular mode, the default mode, which is the batch mode, where you construct a circuit and this doesn't execute anything, and then you execute the engine. Because at that moment, when you execute the engine, only then the RAM in the system is allocated to store the state vector. Then all the operations on the circuit are executed, and after the logic has been processed, you can get access to the state vector, to the simulation object, and then, for example, call print state vector. So one of the two conditions must be true. You either have to be in the direct mode, or if you are not in the direct mode, which is the default, you have to execute the circuit, processes the circuit exactly one time, and then preserves the state vector in the memory. If both conditions are not true, then you will get the following error message. So you cannot access the state vector because direct mode, and circuit execute. One of the two things must be used. If you have done everything in a way that you can access the state vector, then you can not only print or access the state vector by reading it, you can, for example, also collapse qubits, so 4 qubits into a certain state. If you do such modifications, please be aware that after such modifications, the state vector is no longer normalized. So the square of the sum of the square of the complex amplitudes in total is not longer equal to 1. So that's why you need to call normalize. If your modifications are done, then you have to call normalize to renorm the state vector so that the probabilities sum up to 1. And another possibility, you can use state vector raw even in the Python interface. This gives you direct access to the memory in the RAM where the state vector is located. So here on the first sample, you would get a copy of the state vector. Of course, if you're running 39 qubits, you cannot do a lot of copies of the state vector because you don't have enough RAM. But if you use that function, you can map the memory block, which is used in the C++ kernel, directly into your Python address space, and you can access the state vector there as a NumPy array. So you can read it or modify it. Okay, so this was a short and brief introduction into our SDK. We will now discuss a lot of notebooks and samples until we come to the exercise, and you will see all the stuff coming again and again. But I hope now you have we have an impression of how to use our SDK. It behaves quite similar to other well-known SDKs like Qiskit or Cirq. Basically, if you have an SDK which provides circuit-based algorithmics, then these SDK somehow look similar. Do we have a question here? Okay, it was an old one. Good. Then now let's come to the real topic which we want to discuss in that workshop here. We would like to talk with you about algorithms for the NISQ era. So the NISQ era is the era where we have quantum computers which have only a very limited number of qubits. And also the quality of the qubits is not very good. So quantum computers at the moment are not very good, scalable. And we need to think, how can we, with today's quantum computers, how can we achieve quantum advantage for real world applications? So our goal at QMware and Terra Quantum is it to really give industry customers a business advantage today with the technology that is available today. And here, we want to discuss later one sample, which is the traveling salesman problem. And before we can do this, we need to talk about some of the things which are used in quantum algorithms. And one of the building blocks is called a quantum Fourier transformation. So Fourier transformation comes from classical computing. It's used in signal processing or data compression or complexity theory. And here you see the mathematical definition of a Fourier transformation. So the discrete Fourier transformation in the classical world maps values of a vector x into values y by a certain transformation. And this transformation uses complex roots in the plane of the complex numbers. and which are in principle rotations in the complex number. And if we have, for example, like a two-dimensional vector, which would be an analog to 1 qubit, then the rotation would be like 180 degrees. If we would like have a 4-dimensional vector, which would correspond with 2 qubits, then we would have rotations around 90 degrees and so on. And this Fourier transformation, this discrete Fourier transformation, can be transported or transformed into the quantum world one by one. As you can see, the mathematical definition is exactly the same. I will not go too much into the theory and to the details of a quantum Fourier transformation. We somehow expected that you might already know it, but for the ones of you that don't know it, I would like to give a short overview of quantum Fourier transformation and maybe also some ideas how you can understand it from an intuitional point of view. So here you see, and of course, this linear transformation can also be expressed as a matrix. This is a generic form of quantum Fourier transformation expressed by a matrix. And if you do some concrete samples, for example, if you set capital N to 2, so we're talking about 2-dimensional vectors and 2x2 matrix operations, this corresponds to 1 qubit. So this is a 1 qubit system. And if we apply this mathematical definition on a 1 qubit system, we will see, this is the Hadamard gate. So on a 1 qubit system, the QFT is identical to the Hadamard gate. So it transforms a qubit from the computational state into a superposition, into the equally superposition and back. If we would set n equal 4, then we would have a 2 qubit system. And then we have a quantum Fourier transformation, which somehow, as you can see, we have here 1i minus 1 minus I, which somehow represents the 90-degree rotations that I mentioned before in the complex number plane. And for higher numbers, so for higher dimensional qubits, the matrix will grow, and these angles for the rotations will get smaller. And what is it all about? What is the sense, or why do we use, or why do we need this kind of transformation? This is the following. Here we have a system of 3 qubits. Qubit 0 is the least significant bit, and qubit 2 is the highest significant bit. And if we have 3 qubits, or if we have 3 bits, we can express all digital numbers from 0 to 7. And here you can see in this animation how the coding for the numbers 0, 1, 2, 3, 4, 5, 6, 7 could be encoded into 3 qubits. And here we are only using computational states. And if we would measure this system in the computational basis, we would then get a bit string, which describes exactly one binary number or one decimal number, as you wish. And if you convert this system with a quantum Fourier transformation into another base, then you will see that the information is now stored differently. The information is now stored here in the phase. The vectors are all running on the equator, and all the vectors of the different qubits, they have different frequencies. And now you hear the term frequency, and this should remind you of a Fourier transformation, right? In the Fourier transformation, you are transporting time signal data into time frequency data, for example. And this is what you have here. And an interesting point here is that the lowest qubit, the qubit 0, has the highest frequency in the computational base. It flips around for each number when you count from 0 to 7. And here in the Fourier transformation, in the Fourier space, this qubit has the lowest frequency. So it takes the most time for one rotation about 360 degrees. And the middle qubit, of course, has a medium frequency, and here the highest significant bit qubit has the highest frequency, and in the computational basis, the highest significant bit has the smallest frequency. So this is a property of the quantum Fourier transformation. And the quantum Fourier transformation is now able to convert something which is encoded in qubits in the computational basis, can encode it into the Fourier basis, or if you have data encoded in the Fourier basis, you can convert it back into the computational basis. So, any questions regarding that?
Yeah, so there is a couple of questions in the chat. So the first one, I'm not quite sure that I understand it well. So are we quantum Fourier transforming non-commuting variables? So I don't, or states, does it mean anything to you?
No.
Okay, so, and the next one is that, so QFT changes between the computational basis. So is it right?
It's a transformation of the coordinate system, if you want. So this is a different base than this, and we transform values from the computational basis into the Fourier basis, or vice versa.
Great. I think it's fine. Yeah. For the questions.
Okay. Of course. So what you could do if you need a quantum Fourier transformation, what you can do is you can implement it on your own. I mean, you will find on the internet a lot of tutorials and information how to implement a quantum Fourier transformation. Of course, it's such a basic building block that our SDK already comes with an out-of-the-box, ready-to-use quantum Fourier transformation. It's simply called QFT, and the inverse operation is called eQFT for inverse QFT. But our implementation has some additional parameters, which helps you to improve or to optimize performance and resource consumption. Because, as you can see here, this is only 3 qubits. You can see that the rotations on the qubit number 0, the angles which the vector rotates is much smaller than the angle that the vector rotates in qubit number 1 or in qubit number 2. Now, let's imagine we have like a 10 qubit system. If we would have a 10 qubit system, then qubit with the index 0, the angles that the vector would rotate here is 2 pi over 1024. So the angle gets very small. If we have 20 qubits or 30 qubits, the angle gets even smaller. So what we can do is, because of course, there are a lot of operations if we do the quantum Fourier transformation. If you would look on the circuit, which is generated by the SDK, if we do a quantum Fourier transformation, you will see there is a huge number of gates when you have 10 or 20 or 30 qubit system. And therefore it's possible to optimize it, because for more like 10 or 15 qubits, the angles get so close that we could ignore them. We could ignore the rotations with very small angles and just leave them away. And this is possible with our QFT function, so we can set a threshold and we can tell the system, okay, only use the 10 biggest angles or only use the 15 biggest angles and ignore the rest. And this will save a lot of computational power, especially for simulators, but also for QPUs. And another thing is what I said before, like here, the highest frequency is in the qubit number 0, and here the lowest frequency is in the qubit number 0. And this, in the implementation, if you look into the implementation, if you look into the circuit of our QFT implementation, this is done at the end by swapping the qubits. So qubit number 0 and qubit number 2 will swap the positions, and qubit number 1 will stay in place. And this swap operation at the end, you can also control if you want to have it or not, because sometimes it's not relevant for our result if how the order of the qubits, how the qubits are ordered. And if this is the case, then you can save a lot of swap operations at the end if you just turn off the swap or the QFT. Of course, then you don't fulfill the exact mathematical definition, but for many use cases, this is still good enough to get the result that you want. Okay, so that was my brief introduction into the QFT, the quantum Fourier transformation. So now we come to another building block which is also very important in quantum algorithms. It's used a lot of times. For example, it is used with the variational quantum eigensolver, which we will discuss next, and which will be our main application to solve optimizational problems. What is the quantum phase estimation about? You probably know that in quantum computing, in quantum algorithms, we describe operations on qubit systems by unitary matrices. And a unitary matrix has eigenvalues in the form of E2I times theta. And theta is an angle. And the corresponding eigenvector to that eigenvalue is a vector which is part of the orthonormal basis. So that means if we have a state vector, if we have a unitary matrix and the unitary matrix has a number of eigenvalues, then the dem eigenvectors form an orthonormal basis for that matrix. And now you know probably, or you should know from linear algebra, that if you would apply a unitary matrix on a vector, on a state vector, and the state vector is an eigenvector of that matrix, then the result is the same as if you would multiply the eigenvalue with a state vector. The eigenvalue is a scalar, but the unitary operation is a matrix. So this operation is much faster than this operation. So if we have a unitary matrix and we want to execute a unitary matrix on a state vector, and if we would know that the state vector is an eigenvector of the unitary matrix, then we could simplify our computation by just using the eigenvalue, the corresponding eigenvalue, and multiply it with this vector, with this state vector. So that means it would be nice if we could somehow find out, in case we have the state in an eigenstate of the unitary matrix, if we could find out what is the eigenvalue. So the question is, can we somehow measure this value? And the answer is, unfortunately, no. This value works on the complete state. This is called a global phase. And we cannot measure a global phase. So if we have qubit systems which differ only in a global phase, then we cannot see that difference in our classical work, because if we measure those systems, we would get the same results. You can see that when you go to the linear algebra. For example, if you have a state like this one, this is the equal superposition, with 50% probability in the state 0 and 50% probability in the state 1. So that means you get 0 with probability 50% and 1 with a probability of 50%. If you would now have a state which is the same state but multiplied with this scalar number, you can do the mathematics and you will see at the end that if you take the absolute of this complex number and square it, you will get again a probability distribution of 50 to 50. So 50% to 50%. So that means the global phase cannot be measured. But we heard something before. I hope you remember the phase kickback trick, which Rita explained before. We will use it now. So here we have, for example, in that sample, we have 3 qubits, and we prepare these 3 qubits in a certain state we call C. And we have a control qubit. Qubits are always initialized with 0, so we put the control qubit in an equal superposition by applying the Hadamard gate. And now we apply the unitary on this state. And we assume that this state is the eigenstate of this unitary operation. So what we do here now, we execute this unitary operation in a controlled way. So it's a controlled unitary operation that we do perform. And after that, we do another Hadamard on the control qubit. And now you can simply, it's a simple case, you can simply use linear algebra to compute on a piece of paper what happens. So you have the first qubit, the control qubit in an equal superposition, and you have the eigenstate. And so we can multiply, so we can transform this expression to this expression where we have 0 times the state vector plus 1 times the state vector, which are, of course, this is a tensor product. In the second step, we apply the unitary matrix. The unitary matrix, if C is an eigenstate of the unitary matrix, so the result will be we multiply the global phase onto the state vector, but only if the control qubit is 1. So only in the case that the control qubit is 1, we multiply the state vector with that global, with that phase, with that scalar value. In case that the control qubit is 0, we do nothing. And now we do some mathematical transformations. No, sorry. Now we apply the second Hadamard on the control qubit. This is done here. And then we can transform this by mathematical operations into this expression. And now you can see the following. Now we have a relative phase, because in the 0 component, we have the phase 1 plus the eigenvalue. And in the 1 component, we have 1 minus the eigenvalue. And this thing we can measure. And
sorry, Markus, can I just interrupt for you for a second? So there are people in the chat asking if what is a unitary operator here? So I guess it's the ones that you use in the control to unitary stuff.
Pardon, can you repeat the question, please? What is the
what is the unitary in your control to unitary operator? Is it the QFT unitary, or what kind of unitary?
No, it's any unitary matrix.
I guess it should have C as its eigenvector as well.
So it can be any unitary matrix which describes some operation. It could be a rotation over the x-axis, for example.
Okay.
Yeah. So we want to apply any operation which is described by this unitary matrix, and we assume that the system is already in an eigenstate of this matrix. And the question is, if this is the case, can we measure the eigenvalue by measuring the quantum system? Can we get access to the eigenvalue by measuring the quantum system? This thing for itself does not solve any problems. Yeah? It's just a building block. We will see later where we use it. Now, what I want to explain here is only you need to understand why does the quantum phase estimation work? What we want to do is we want to find a way to be able to measure global phases. We cannot measure global phases directly. So what we do is we do a trick. We do not apply the unitary, we apply it in a controlled way. And the phase or the effect that the unitary should have on the state vector is kicked back into the control qubit. Here's our state vector, the original state vector, it's not cut. And here you see the phase, which would be a global phase of the unitary matrix, is now a relative phase in the control qubit. A relative phase, why? Because here it's 1 plus the scalar, and here we have 1 minus the scalar. And this is not a global phase, because the phase is different for the 0 component and for the 1 component of the control qubit. I hope this makes it clearer. And now we can start measuring the control qubit. And as you can see, there's a different probability of measuring 0 or of measuring 1. The probability of measuring 0 is 1/2 times 1 plus this scalar value, the absolute and in squares. I have a key. Thank you. And the probability of measuring 1 is 1 minus the scalar value. So we have different probabilities. So if we measure this circuit, the control qubit, multiple times, then we can find the eigenvalue or an eigenstate of a unitary matrix. So this is the message. But the message is also, if the angle theta of this scalar value is small, then the difference in the probability for measuring 0 or measuring 1 is also very small, which means we need to repeat the experiment a lot of times until we see a probability distribution, right? I mean, here if the theta is 1 degree, then the probability for measuring 0 is 0.9999, and the probability for measuring 1 is 7.6 to the power times 10 to minus 5. So this is so we would need to measure the circuit 1 million times maybe, or 10 million times to really get a significance in the statistics, to really be able to measure that probability and therefore to measure that eigenvalue. So I hope if there are any questions regarding that, would be good to get them now.
I think it's okay now. So
okay, we are only on the left part of the slide at the moment. We don't look on the right part. It's only the left part at the moment. And this circuit here is described by linear algebra, and it shows you that with this phase kickback trick, we can transform a global phase into a relative phase in a control qubit, and then measure out the difference. But of course, we need a high number of repetitions of the experiment to be able to measure small eigenvalues. Okay, if this is understood, now we can make another trick. The next trick is to be able to get a better precision so that we don't need to measure that often. What we can do is we can increase the number of control qubits. Because this is our measurement register. Here we have a measurement register which contains only 1 bit of information. At the end, we get a 0 or a 1. Yeah? And we need to repeat the experiment 1 million times, and then we get a probability distribution for 0 and 1. Now we increase the number of qubits in that register, which we measure. And what we do now is we are now working with different powers of the unitary. Yeah? So on the lowest qubit, we apply the unitary 1 time. On the next qubit, we apply the unitary 2 times. On the next qubit, we apply the unitary 4 times, 8 times, 16 times, 32 times, and so on. So we are working with the powers of the unitary, and we do it in a controlled way. And of course, you can imagine if we apply a unitary 2 times or 4 times or 8 times, the effect is bigger than if we only apply it 1 time. So that means here we are creating this kind of operations in a system with powers by 2. And we encode it in the phase, as you can see here. And encoding something in a phase with different powers should remind you of something. It should remind you of the quantum Fourier transformation. Here you see the encoding of a decimal number between 0 and 7. And as you can see, here we have different powers of the phase. Yeah? Here we do small rotations. Here the angle is double, as in the qubit left. And here the angle is 4 times as big in the first qubit. These are different powers of applying the effect of the operation onto a qubit. So the conclusion is, what we are doing here is we are computing the eigenvalue, but in the Fourier basis. And if we have something encoded in the Fourier basis, we need the inverse Fourier transformation to bring it in the computational basis. And now we can measure the computational basis, and then we can measure the angle theta multiplied with a constant. The constant is 2 to the power of t, and t is the number of qubits in our measurement register. So we get the result, we divide it by 2 to the power of t, now we have theta, and then we can compute e to the power of I theta, and we have the eigenvalue of the eigenstate belonging to that unitary operation. Now I wait for if you say there are some questions.
Yes, so there is a question. So if I have a state with a global phase, using the record on the left can exactly evaluate this global phase?
It can evaluate with a certain precision. I mean,
okay.
What I do is, the trick is, as I cannot measure the global phase, I build a circuit where instead of having a global phase, I push the phase of the unitary matrix only into the one component of the control qubit with different signs, with the plus sign and the minus sign. And therefore, now I have a relative phase, because now it's not longer a global phase, because I don't multiply the scalar with the qubit with index 0. The complex amplitude for the 0 component and for the 1 component is different. So now I have a relative phase. And relative phases is exactly what I can measure in quantum systems. Because now the probability between getting 0 and 1 is different. And therefore I can measure it.
Okay, so there is one another question. So what is the order of the numbers of operations needed? I guess it's in terms of elementary operations in the quantum circuit?
Does the question refer to the exponent of the matrix?
I think so, yeah.
Yeah, so this is the encoding in the Fourier basis. We apply the unitary matrix one time and we get a small effect on this qubit. We apply it two times and we get a bigger effect on the next qubit. The effect is 2 times bigger than on the previous qubit. We go to the next qubit and we apply now the unitary 4 times. So the effect is 4 times. Then we do it 8 times. The effect is 8 times bigger. Then we do it 16 times and so on and so on. So each qubit I climb up here in the ladder, I double the number of executions of the unitary. So I also double the effect. And therefore, and this is exactly how the Fourier base encoding was described here. Yeah. For each qubit, when I climb up the ladder, for each qubit, the effect gets bigger, the effect gets double. Here we have rotations across, what is it, P over 8. Here we have rotations about P over 4, and here we have rotations P over 2. Sorry, this is P over 2, and this is P over 4. But you see, the rotation here is 2 times faster than here, and the rotation here is 4 times faster than here. And this is exactly what we are doing here. We apply a unitary on the lowest qubit, we apply it on the next qubit 2 times, then 4 times, then 8 times. And this is how we encode this information. We encode this relative phase in different powers into our qubit register. And then we use inverse quantum Fourier transformation, and then we get a bit string in the computational basis, which gives us a number which is proportional to the angle which defines the eigenvalue.
Okay, so we probably should move forward because we don't have so much time and we still have a lot of stuff to cover. So
okay, and these are 2 building blocks, yeah, and you will see how we later use these building blocks, to build a variational quantum eigensolver. Because with the quantum phase estimation, I have not won a lot, because it only works if I have a unitary matrix and I know the eigenstate already, and also I can prepare the eigenstate in that qubit system. If I can do all of this, I know the unitary, I know the eigenstate, and I can prepare the qubit system in the eigenstate. Then with this trick, I can measure the eigenvalue. But if I do not know the eigenstate of the unitary matrix, then this doesn't help me, okay? But if I know the eigenstate, it helps me to get the eigenvalue. And you will see how we later will use that to implement a variational quantum eigensolver, which finds out the eigenstate and the eigenvalue of any unitary matrix. So this is just a building block we need later. Okay, so then now we have set up the scene, we have set up the stage, and now we would go on, and now we come to the start, and now we come closer to what we really want to do, because we really want to implement something which does something. We want to implement something which can solve, for example, combinatorial optimization problems. And therefore, Margarita, we need something which is called...
Yes, so we need something which is called variational quantum algorithms. So what is so particular about variational quantum algorithms? So in the you have seen before that you had this great circuits, and in each circuit, each of the unitaries that you applied was a very precise unitary that you were planning to do, and you knew in advance what kind of unitary you want to apply. However, like it turns out that with this kind of approach, there is a lot of stuff which are difficult to solve. And in addition, like with this computation where each of your unitary is a very precise and you really rely on the computation to be exact, like you need this fault tolerant quantum computer in order for making things working. So now what we suggest instead is that we do not use a circuit which is fixed, but we instead offer a circuit in which some of the gates depends on some parameters. And like with this, you can imagine something like a neural network where the weights of your neural networks is something that you're going to settle later. So a machine learning model, when you say that, okay, your model is a linear regression, however, the exact coefficients of your linear regression going to be something that you're going to find later by optimizing the parameters of your model. So an ansatz is a model, is a circuit in which some of the parts depends on the parameters. And so the purpose of variational quantum algorithm is just to settle the value of these parameters. So basically you do the same things that you do in machine learning, is that you try to train your quantum circuit, which like somehow depends on parameters, and you try to force it to solve the problems that you want to solve. So when we speak about training, there is usually there is like an unavoidable part, which is the cast function. So the cast function basically is something that helps you to say, okay, so this value of a parameter is better than another value of a parameter. So, and it turns out that like in this variational quantum algorithms, you have two parts that interact with each other. So the one part is the part which tries to optimize the parameters of your quantum circuit. So, and this part is often done with some classical optimizer, like the ones that you use for the machine learning, or the ones that you use in classical optimization. But what requires a quantum computer, for instance, is the evaluation of the loss function. So now let's say that you suggest some values of the parameter for your quantum circuit. So then you need to decide if these values of parameters do or do not do like what you wanted them to do. And for this, you launch your circuit on a quantum computer and you get an output, which is the value of your loss function. So maybe what is cool about this stuff is that actually when you proceed in this kind of training loop, you can also learn and somehow circumvent some hardware imperfections. So for instance, if one of your qubits is like super biased and so on, so then the parameters that you're going to find for your quantum circuit going to change accordingly during your optimization process, and still like you're going to get a valuable result out of your quantum computer. So yeah, and when you try to apply these variational quantum algorithms to a problem of from the optimization, like to find a good schedule or to color a graph or to whatsoever, so the cost function that you minimize is related to the problems that you try to solve. And so the next slide, we're going to see how they are related to each other. So for instance, like the kind of basic problem of combinatorial optimization that people look at is the problem of the maximum cut. So in this problem, what do you have? You have a graph, so in which nodes are connected to each other, and you want to split the set of nodes on two parts. So in which and you want to do it in a way that the number of edges that goes from one part to another part is as big as possible. So this is a typical combinatorial optimization task. And basically what you can do is that you can introduce one variable per vertex. So if it gets the value 0, then it means that it belongs to the left part. If it gets the value 1, it means that it belongs to the right part. And then you can write the problems that you want to optimize as like with the objective function, where you maximize over the values of your variables some functional. So basically, when we go to quantum computer, it makes actually more sense not to speak about the binary variables which take values 0 or 1, but rather by with
sorry, Rita, we mapped it to -1 + 1 here in the slide, not to confuse the attendees.
Yeah, so you use a -1 and +1. Yeah. Basically, it's not difficult to go from 0 and 1 to
exactly,
-1 and 1.
The product is not 0, yeah. And it maps better to the eigenvalues of that. Yeah. Sorry.
Yeah, so then let's say that you can use a different encoding. So you can encode like left part by like +1, right part by -1, and then you can write also the functions that you want to optimize. And like now the question is how you can translate it to a quantum. So basically, when you want to solve an optimization problem with a quantum computer, you need to map your instance to something which is called a Hamiltonian. So Hamiltonian is a Hermitian operator. And in this Hermitian operator, what you want to achieve the correspondence between the eigenvalues of the Hermitian operator and the values of the functions that you want to optimize. So basically you map each of your variables to one qubit. So now each of the readouts of the qubit are going to correspond to one particular solution. So for instance, like 0, 1, 0, 1 going to correspond to the values of the variable -1, 1, -1, -1. And then like this is going to correspond to the solution of your optimization problem. And now like you wanna design a quantum operator in a way that when it acts on the register, like when it acts on this like 0 on the states of combinatorial of the computational basis, the corresponding eigenvalue corresponds to the value of the objective functions that you want to optimize. So, and it turns out that when you use these variables, like when in your initial formulations, you use the variables -1, you use the variables that take values -1 and 1 to like to define two different parts. Like when you go to this Hamiltonian, you basically just need to replace them with Pauli Z's acting on the corresponding qubits, and you get the required Hamiltonian. So basically, for the maximum cut, we are done. We just got the objective function, we replace the stuff, and then yeah. And so now what happens is that you get this Hamiltonian. So this Hamiltonian is defines the problems that you want to solve. So then you use your variational ansatz in order to prepare a quantum state. So then you measure your quantum state, and basically the readouts, the measurement results correspond to a solution of your optimization problem. So you got some qubit values, and you say that these qubit values correspond to a partition of your graph in two parts. So okay, maybe Markus, you wanna add something?
I just want to add one thing. I hope this term here reminds you of something. If I go back, it looks a little bit like this, right? This is an operator, it's a unitary operator, and this is a scalar. And here, the C is an operator, a quantum operator, so it's a unitary operator. And this is a function which gives us a scalar. This will be important later. Just wanted to draw your attention to that. And one more cool thing is that this Hamiltonian comes from a classical problem. So the eigenstate, if we would know it, the eigenstate of this Hamiltonian would be in a computational basis state. That means we can measure it with certainty. Just a detail. Okay. Shall I go to the next slide, Rita?
Yeah, I think that, and basically, yeah, so now maybe just to add a little bit more explanation how it's all related to the traveling salesman problem. So traveling salesman problem is also a problem of combinatorial optimization. And so what we're going to see is how you construct this Hamiltonian of a traveling salesman problem. So as the ones that we've seen before on for the maximum cut, which is kind of trivial, but for the traveling salesman problem, it's going to be a little bit more involved. And so by using this, you can then apply the variational quantum agent solver and get your result. Okay?
Yeah. And the variational quantum eigensolver is now an algorithm which helps us to find the eigenstate and also the eigenvalue of this Hamiltonian, of this Hermitian operator. So what is the variational quantum eigensolver? So it's a hybrid algorithm. It uses classical and quantum parts to find often large matrices. We call the matrix H. We try to find the eigenstate and the eigenvalue. This only works for unitary matrices because we can only implement unitary matrices in quantum algorithms. But if we have that, then we can use the eigensolver, the variational quantum eigensolver, to do that. And why does this work? It works because if we have any state vector, this C here is a state vector and it depends on parameters. This is what Rita explained before with the variational principle, with the variational algorithms. We use a circuit which is controlled by parameters. And the circuit, of course, results in a state vector, in a quantum state. So we have a quantum state which depends on parameters. We have this matrix H, where we want to find the eigenvalue and eigenstate for it. And now we are computing the expectation value. So this is the mathematical definition of the expectation value. We take the complex conjugated and transpose of the state, multiply it with the matrix, and multiply it again with the state, and then we get the expectation value of this Hamiltonian, of this operator, H. And now there's one principle, the variational principle. The variational principle ensures that this expectation value is always greater than the smallest eigenvalue of H. So now, if I turn around this conclusion, if I would find the lowest expectation value by changing the parameters of the state, then I would have an eigenvalue. And if I would have an eigenvalue, then this state here is an eigenstate of the operator. So what the variational quantum eigensolver does is now the following. It guesses any vector, it guesses a state vector by guessing some parameters. It could be random, for example. We choose a random set of parameters, so we get any random state vector in our system. Now we compute the expectation value, and we notice this expectation value. We write it down. Now we modify the parameters and compute the expectation value again. If the new expectation value is lower, then it's good. Then we throw away the other one and we continue. And so we try to find the minimum expectation value by modifying these parameters. And this is done by a classical optimizer. So the classical optimizer tries to find a set of parameters so that the expectation value reaches a minimum. And if we find the global minimum, then we find an eigenvalue of this operator. And then the state vector that we prepared, which gives us this lowest eigenvalue, is an eigenstate of the matrix. So it is a possibility, as Rita explained, it is a possibility by training our circuit, our parameterized circuit, to find the right parameters, that we get the lowest expectation value, and then we have an eigenvalue and an eigenstate of any Hermitian or unitary operator. Okay, now you might ask, okay, now I said we found the lowest eigenvalue. unfortunately, here we have an optimization problem where we need the highest eigenvalue and the highest eigenstate. This is easy. If we have an optimization problem where we should maximize something, we multiply everything with -1, and then we have a minimization problem. So we can transform any maximization problem into a minimization problem just by multiplying it by -1. Okay, so this is the idea. Yeah, we have a circuit which can produce any state vector that we want in a high-dimensional space. Yeah? If we have a state vector of 3 qubits, we have 8 dimensions. So we can rotate the state vector anywhere by using these parameters, and we can compute the expectation value. And if we find a minimum, a global minimum for the expectation values, then we have found the eigenvalue of this operator, and therefore we have also found the eigenstate. And if we found that, we found the solution for our optimization problem, because the vector x, which is the lowest eigenstate, is the solution for a minimization problem. I hope now somehow the loops get connected. And how do we do that? We use quantum phase estimation. Yeah? We just assume for every vector we have, we just assume, oh, this is an eigenstate. And if this would be an eigenstate, we can compute the eigenvalue by using quantum phase estimation. This is another way to explain it. Yeah? And then we try to minimize it, and if we find a minimum, then we have a real eigenvalue, and therefore we have a real eigenstate, and the eigenstate is the solution of our optimization problem. Okay. If there are some questions in your mind now, I would expect that. I hope they will clarify as soon as we go to the sample and really look how it works, okay? So, and now the problem is, or the challenge is, if we have a problem like this, how can we come to a Hamiltonian? Because if we have a Hamiltonian, we can use the variational quantum eigensolver to find the lowest eigenstate and eigenvalue of this Hamiltonian. But how can we get an Hamiltonian for, let's say, in general, for optimization problems? And one way to do this is to use the QUBO formalism. The QUBO formalism says, if you have a binary quadratic function, so you have variables x1, x2, x3, which are binary, they have the value 0 or the value 1, and they are either linear or in a quadratic form. Here we have quadratic parts, like x1 times x2 is a quadratic term. Here we have linear terms. The cool thing about binary variables is that if I square a binary variable, the value does not change, because 0 squared is 0 and 1 squared is 1. So instead of writing -5x1, I could also write -5x1 squared. And if I transform all these values into quadratic form, then I could write this formula also as a matrix. And I multiply a vector x1, x2, x3 in transposed form or in regular form. And then if I multiply that, I get exactly this term. You can try it out, okay? On the main diagonal, you see the coefficients -5, -3, -8, where we have x1 times x1, x2 times x2, x3 times x3. And here we have the 2 and the 2 together gives this 4. Yeah, this is 2 times x1 times x2, and this is 2 times x2 times x1. So multiplication is commutative, so it's 4 times x1 times x2. And then we had 8 times x3, x1, x3. We split it up for x1, x3, 4, x3, x1, and so on. So we can write this expression as a matrix. And this here is, if we are talking about real numbers, this is the complex conjugated and transposed form of this vector. So this expression is equivalent to an expectation value of a quantum system. And this is what we exploit. And now I would like to switch to a sample where I show you first, in a very simple sample, how to use this QUBO formalism to solve problems by calculating such a Hamiltonian and then using a variational quantum eigensolver to find the lowest eigenvalue and the lowest eigenstate. I hope you are fine with that. And now I would end the slide presentation and I would switch to our notebooks. So, Rita, can you see my browser now?
Yes,
Okay,
everything's
good.
fine. Yeah, we can see it.
So, if you go to our system, you will see a look like this. This is all standard content. We have a lot of tutorials and experiments that you can use. And here is one folder, it's called WOMANIUM exercise. There you will find the traveling salesman problem. But for the start, I would like to go to a simpler problem. I would like to show you a very simple QUBO use case. So what we want to do is we want to implement a variational quantum algorithm by having a circuit which uses parameters. And this theta is a vector of parameters. And depending on how the parameters are set, this circuit moves the state vector in a certain position in a highly dimensional space. And then at the end, we do a measurement. And with this loop here, we compute for a set of parameters, we compute the expectation value. And this expectation value goes into our classical optimizer. And the classical optimizer now tries to find a set of parameters so that the expectation value reaches a minimum. And if we find the global minimum, then we have found an eigenvalue of the unitary operation, which is described by this ansatz. And so there is a loop trying to find the minimum. So this is everything we have talked so far. And now we see exactly the problem that I showed in the slides. We have this expression here. It's a quadratic function with binary variables. We can write it as a matrix. And then this could be interpreted as the expectation value of this matrix operating on this vector. And the cool thing now is that if we do this, we get a Hamiltonian operator, and with our variational quantum eigensolver, we can then find the lowest eigenstate and the lowest eigenvalue of this operator. Okay, let's do it. So first, if not already installed, we need docplex. Okay, now, as I said, we use a module which is called basic.algorithms.QUBO. This module allows you, via a programming language, to build up such a quadratic function. Okay? So we import this module, basic.algorithms.QUBO, and then we create a quadratic function and give it a name. And now we try to implement the problem which I showed you before. We try to implement, sorry, this term. Okay? So I go to our QUBO model. Oh, sorry. There's a latency, I don't, yeah. We go to our QUBO model and I add 3 binary variables, X, Y, Z. They are of type binary and can have the values 0 and 1. And then first I create the linear part. So minus 5x minus 3 epsilon minus 8z. And then the quadratic part, plus 4x times y, plus 8x times z, plus 2y times z. And this should be exactly this term. Okay, x1 is equals x, x2 equals y, and x3 equals z, okay? And the minimum solution for this problem is -9. And this is this is how I have to set the 3 variables, x1, x2, and x3, to get the minimal solution. So our optimization problem, this would be the exact solution. It's a simple problem. I can compute it in my head. And now I implement this as a quadratic function. And then I tell our system to transform this into a Hamiltonian. So now what the system does is maps the binary variables to the eigenvalues of the Pauli Z operator and builds up this Hamiltonian, which we were talking about. So here you see the Hamiltonian. It's a linear combination of Pauli Z operators on different positions and the identity operator. This is our Hamiltonian. And this offset here is a constant value, which we will need at the end to compute the exact eigenvalue. Okay, so I can execute the cell. And then I get this result. Now I can also print this quadratic function, and we'll get this information here. This is the objective where the B implement. These are the bounds for the variables, and it's binary variables, and the variables are called X, Y, and Z. So in the next step, we first we need a circuit. Right? We need a circuit for our variational quantum algorithm, a circuit which has parameters, which is able to produce any state like this. So you could now sit down and think about it and implement such a circuit on your own, or you just use our SDK. There's a function or an object which is called QLocalCircuit parameterized. Here you can give some parameters into that class, and this automatically creates you a circuit with parameters which is able to, in a smooth way, reach possibly all the points in our high-dimensional sphere. And the parameters you need is, how many qubits do we have? What kind of operations do we want to have in our circuit? What kind of rotations? And what kind of entanglement do we want to have? And how often do we want to repeat the rotation block and the entanglement block to produce this circuit? Okay, I think the best is I show you the result. So I execute this. I execute the cell, and the result is now a circuit. You see, the circuit has rotations around different axes and entanglements. And then again, another block of rotations and entanglements and another block of rotations. So the block of entanglements and rotations is repeated 2 times. This is what we say here with number of repetitions equals 2. And as I said, this is a parameterized circuit. It has a lot of parameters. So I also need a vector which contains values for all these parameters. So here I just create a vector with random values. Okay? And for the random values, I construct the final circuit and draw it. So it was just for drawing so that you can see how this looks like. So again, I execute the same cell just to show you again. So this is our parameter vector with random values as a starting point. Yeah. And I feed that into the circuit, and then I get this kind of circuit. This is our ansatz for our variational algorithm. And now I need the variational quantum eigensolver. This is also a ready-to-use function in our SDK. You just pass in the engine where you want to execute it. You pass in the Hamiltonian, which you want to solve. You pass in the circuit, which forms our state vector, and you pass in the initial parameters. And then you call run. You say what function to use to compute, what optimizer to use. Here I use a classical package SciPy, and it has a minimize function, and this minimize function supports different methods. There are different mathematical methods to find minimum values in such an optimization problem. So this is purely classical. And this I can start and execute. And I will do so now. Now you see the optimizer starts. It's very fast. It does 2,000 evaluations of the circuit. So it calls the circuit with 2,000 different set of parameters. And then it says, oh, I have found the minimum, the lowest eigenvalue of this operator at minus 4.5. And it took 1 second, and I took 1,800 operations per second. And this is our eigenvalue, and this is our set of parameters for the circuit. These are the parameters which give us the optimal solution. So the value that the optimizer found is minus 4.5. Now, if I compute the exact eigenvalue with a NumPy linear algebra library, as you can see, the exact result maps completely to what our optimizer has found. And here the parameters 4.5, here it's 4. It must not be the same. It can find different kind of eigenvectors, but the eigenvalue is the same. So, and how now do I get the solution? I have found a minimum for the eigenvalue. I have found the parameters for the circuit, which give me the eigenstate. So if I feed in these parameters into our circuit, then the state vector is prepared in the eigenstate that corresponds to this eigenvalue. So what I need to do is, I create a circuit, I take my variational form, and I tell them construct the circuit, and as parameters use the result object of my optimizer. And there in the component X, I get these numbers here. And so I construct the circuit, I do a measurement, and then I execute the circuit only one time. As I said before, this is a classical Hamiltonian. So if I have found the eigenstate is in the computational basis. And therefore, if something is in the computational basis, I can measure it exactly with exactly one measurement. So I do a measurement, I execute the circuit only one time, and then in my classical register, I find the solution of my problem. Set variable x to 0, variable y to 1, and variable z to 1, and then my result is -9. And if I do this with the thing that I computed with our variational algorithm, the result is -8.99999, which is very close to the exact result. And why is it here -9? And here we said we found the eigenvalue -4.5. This has to do with the construction of our Hamiltonian. The Hamiltonian for this problem looks like this, and it has an additional property, and the additional property was the offset. The offset is also -4.5. So we need to add this offset on the eigenvalue of this Hamiltonian to get the eigenvalue of the problem. And now we have solved this optimization problem. So now, let's see if we have some questions, Rita.
Yeah, we have some questions, but more about like implementation stuff and so on, about the derivative-free optimization, derivative-based optimization. So these are advanced questions. So
okay,
I'm taking care of them in the chat. So
okay.
I'm probably going to forward you one or a couple.
Yeah.
But they're not about code and.
Okay, because we need to. I'm sorry, we need to look a little bit on the time. Okay, so this was just how to show you how you use our QUBO module and how you use our variational quantum eigensolver to solve a very simple sample like this. But now we want to solve something more challenging. We want to solve the traveling salesman problem. And I have prepared 2 files for you. So the ones of you who will get access to our system will find these files in that folder here. And it's the exercise, and this is the ready solution. It's fully implemented, and this is the exercise where you can try on your own to solve the problem. So as we have not so much time, I will start here, but then later switch over to the solution, because I think 30 minutes is not enough for me to implement everything from in the exercise. So I will start here, but then we will move to the solution, and I will just discuss and show you the solution. Okay. Solve the traveling salesman problem. What is the traveling salesman problem? The traveling salesman problem is we have a set of locations, and between the locations or between the cities we have a distance, right? And now we want to find a route, for example, a route so that we reach every city exactly one time, but we want to minimize the total distance that we have to drive. This is a very common problem, optimization problem in logistics. Yeah? We want to minimize the kilometers that a truck has to drive to deliver all the goods to all the different depots of the stores. So we can express this problem as a quadratic, unconstrained binary problem. And to solve it, I use a very simple and intuitive approach. It's already surprisingly complicated enough, but of course we can do it in a more efficient way if we put more intelligence into the creation of the formalism. But now for the start, I would like to use an intuitive approach. The intuitive approach is the following. I invent a binary variable which has 2 indices, x, I, j. And xij is 1 if the depot with number e is at location j in our path for our cycle. and 0 otherwise. And if I do it like this, then I can express a path by a matrix. This is the path starting, so the index j is 0, starting with depot 0. Then index j is 1, moving to depot number 2. And then index j is 2, moving to depot number 1. So with this matrix, I can describe a route going from depot or city number 0 to depot or city number 2 to depot or city number 1. Now imagine that I have a matrix W with 2 indices, which describes the distance between all the cities. So if I know my path, and this binary variable says, where will I start, where will I go first, where will I go next? Now I can multiply these variables with my weight. The weight is the distance between 2 cities or 2 depots. And if I make the sum, I can define a distance function. So this gives me the distance, and this is just a factor. I need the factor later for my optimization problem to give that distance a certain weight in my total algorithm. So this is the first part. Okay. Now, if you think this is enough, unfortunately, it's not, because if we would give this distance function into a variational quantum eigensolver and tell him, please optimize this function, he would probably come up with a result. If you don't move, if you don't drive to any city, then your distance is 0. Okay, this would be the smallest distance, and the solution would not be satisfying, right? Okay, so we need additional terms in our cost function. We need to define some constraints. What are the constraints that we want to enforce? The first constraint is we want to visit a depot only 1 time. We don't want to visit the same depot 2 times or 3 times. That doesn't make sense. So we want to visit a depot maximum 1 time. And we want to visit a depot also minimum 1 time. We don't want to skip a depot. Yeah? So what we do is now we also define some penalties for our distance function and saying not only the distance function must be minimized, but also these terms must be minimized. And what are these terms? So when you look on this term here, on the first term, what is it saying? It's saying make a sum over j. J is the number of locations or positions in our path that we drive. For a given j, go over all the cities. I iterate I from 0 to n minus 1. N is the number of cities. And I ask the binary variable, is this city with index E on the j position on our path? If there is exactly 1 city on the position j in our path, then this sum here is equal to 1. If I subtract 1 from it and I square it, then I get a 0 if exactly 1 city is in the path at index j. If we have 2 cities here, then this term is not 0. And if we have 0 cities lying on our path, then this term is also not 0, then it's negative. We get rid of the negative sign by squaring this, and therefore this term here gives us a 0 if there's exactly 1 city on each location in our path. This is the first constraint. The second constraint is vice versa. Here we check if each city is used exactly once on our path. Here we checked if on each position in our path there's only exactly one city. And here we check if each city is used exactly one time on one of the positions in our path. And here we have another scaling factor. Here we have the scaling factor B, and here we have the scaling factor A. Why is this important? Yeah, at the end, our cost function is the sum of this constraint, and of the distance. And if we give too much focus on the distance, our optimizer tends to find solutions which minimize the distance, but ignore our constraints. But if we give too much power to the constraints, then our optimizer will find solutions which fulfill our constraints and ignore the distance function. Yeah, if this constraints weigh 100 times or 1,000 times more than the distance, then the distance will not play a big role in our optimization problem. So what I want to say—
sorry, Marcus, can I interrupt you just for a second? So we had
Yes.
a question, why we put our penalty terms in square forms. Actually, like what we want from our penalty terms is that when the solution is a feasible solution, so for instance, the values that you give to your X values correspond to a valid answer to a question, you want this penalty term to be 0. So it means that you do not increase costs for the solutions that work for you. But the purpose is that when your solution doesn't fit the constraints, you increase, like the cost function going to be big, so it's going to be much bigger than it's now. So that's why you get the square. So basically in the square, if the term inside the square is 0, so it means that your constraint, your equality is satisfied, so then your penalty is 0. However, when it's not 0, it gets like a positive number, which is large, and so that way you kind of is the solution becomes highly suboptimal, so your solver not going to return this solution.
Exactly. Very good. Yeah, this was a perfect summary, Rita. Thank you very much. And we need to ensure that our factors, which we put on the constraints and on the objective, they are in balance. They need to be in balance. So the penalties should have the same range of numbers than the cost function. And a good thumb rule is like this. So if you multiply B times the biggest value in our matrix that holds the distances between all the cities, this should not be bigger than this one here. This is a good thumb rule how to balance the factors B and A, and then we get a cost function which is a good objective for our optimizer. So and now. So this was the explanation, the introduction into the TSP, and now we come to the details. So this is our problem. We have 4 cities, and here we have the distances between the cities. Of course, this is not realistic. It's very explicit, the difference, so that we get good results. And one second. Before my, okay, and yeah, this is what I need to do. I need to implement this distance function, and I need now to put this cost function, which consists of this term HA and HB, into our code. So this is our Hamiltonian. Here you see the first constraint, the second constraint, and this is our distance function. And this is what we want to implement with a QUBO formalism. Okay? And here's some more details about this scenario. I also tell you, please note, if you have this expression and you multiply it, yeah, you solve this square over the sum, you get a term like this and some constant. And this, and this constant here we ignore, because if we have a constant somewhere, yeah, it doesn't have an effect on our optimization problem, because the constant does not depend on the parameters. So we can ignore constant parts in our terms, and we just implement these parameterized parts in our code. Yeah, and this is the exercise notebook. Yeah, this is a skeleton where you can start to implement the problem. You can choose the alpha and beta factors for the two constraints. You can here enter the values for your distances between the cities. And then you need to build up your quadratic function with variables, with linear terms and quadratic terms, and so on and so on. This is the exercise which you can do. And because I look on the time now, I will not, my plan was to show you how to implement it and really typing in all the things, but I cannot make it in the time. So what I do instead is I go through the code with you of the solution, and you also have the solution in case you want to do it on your own, and just execute it and discuss with you how we implemented that with the QUBO. So this is the problem. This is our Hamiltonian, which we want to implement. And now, first I define my alpha 1 and alpha 2, which is basically, this is alpha 1 and this is alpha 2. I set it to the same values because normally both constraints have the same importance. If I would have constraints which have different importance, then I could choose different values, but for traveling salesman, it doesn't make sense. So I set alpha 1 and alpha 2 to 10, because the biggest value here in my distance matrix is 9. And if I set beta to 1, beta times 9 is 9. And so choosing 10 as a value for alpha is quite a good value. Now I create my quadratic function. First, I create all the variables. So here I choose a very primitive approach. Yeah. I have a binary variable with 2 indices. That means for 4 cities, I need 16 qubits. Yeah? This is not a very efficient way of encoding the problem, but it helps us in understanding this logic. We have better ways to encode it and to save the logarithmic number of qubits. But here with this very intuitive approach, we choose 16 qubits if we have 4 cities. Because for each combination of I and j, we take 1 qubit. So we have a loop for j from 0 to n-1, for e from 0 to n-1, and we add variables, and the variables we name x, I, j. Now let's implement this part here. Here we have a loop over j, a loop over I and k, and then for all combinations of I and j plus 1, we multiply it with the distance value in our matrix. So we have 3 loops, looping over j, looping over I, and looping over k. And here I say the variable xij multiplied with the variable xkj plus 1 gets the value of our distance. This is our matrix, and this is the row and the column in our distance matrix. Why is this modulo n here? because j runs from 0 to n minus 1. J plus 1 can become n. J plus 1 in our sample can become 4. But our indices are only valid from 0 to 3. This is the connection from the last city to the first city. So our path, so starting at the first city, take a path over all cities, and then come back to the first city. This is why we have this modulo n here. If we don't care where the path stops, if we don't care if the truck stops at the last depot, we could limit running j from 0 to n minus 1. Then we would skip the last connection from the last city to the starting point. But in our case, we want to have a closed loop, and the truck at the end should be in the starting point again. And then we need this modulo n here. And if I let it run, I'm not sure if I executed this one. Now I let it run, and now you see I have my variables. We have 16 variables named with the indices j and I. And this is my objective. Here I have my quadratic parts for implementing the distance function. Now, in the next step, I want to implement my constraints. Again, I have two loops from j over j and over I, and here over I and over j. And please note that this term here, the square of the sum over I minus 1, if you multiply it out, if you do the algebra, then you get this term with a constant. You can do it on a piece of paper for 2 or 3 binary variables. You will see that this is the generic form. And this is easier to implement than this one. And now I need to implement this. So I have a sum over j running from 0 to n minus 1. Then I have a sum over I and a sum over k. In the sum over I add just this xij. I'm doing this here. Xij equals xij minus alpha 1. Why? Because, of course, we could already have, this variable could already have a value. So I need to get the value first. If this variable does not yet exist or does not have a value, I take the value 0. I subtract alpha 1 from it. And then I have implemented this part over all j's. And then comes the quadratic part here, this one. I have a loop. I turned around the indices in the code, it was easier. So I start k at I plus 1, and it runs until n minus 1. And then I say xij times xkj. I look if this expression already has a value. If yes, I get it. If no, I set it to 0. And I add 2 times alpha 1. 2 times alpha 1 on this part. Okay, this is the implementation of the first constraint. This is the implementation of the second constraint. It's identical. I just switch the loop for I and the loop for j. And then you see my objective gets bigger. I have now more terms. And now I do another constraint, just for you as a hint. If you have constraints like this, for example, if I have the constraint that my truck should start at the 0th point in my path with a 0 city and go from there to the first city, if I already know the first part of the route, I can add another constraint and can say, if this variable is true, I give it not a penalty, I give it a negative penalty, which is a bonus. So I subtract something from my value, and if I have a minimized problem, this will help me. So this is not a penalty, it's a positive, it's a bonus, because I subtract something from my objective value. To start with the first city at the first position in my path, and then go to the city with index number 1 in my second position in my path. Again, I extend my quadratic function. And now I compute the Hamiltonian. And the Hamiltonian looks like this. It's a linear combination of a 16-qubit Hamiltonian with different I and Z operators. Quite complicated. So this is the Hamiltonian that we need to solve. And now I do the same as before. I don't know anything about the good starting point for our parameters. So I just choose random starting parameters for our circuit. Here, to get the same result when I run the cell again and again, I have initialized the random generator with a certain number. And now I wanted to show you that our optimizer library, SciPy, has different methods that we can use. I have chosen one of the methods which gives quite good results and doesn't take so much time. It's called SLSQP. Here I said a little bit about some of the optimizer methods. And then I construct a circuit again. Yeah? The circuit here, the ansatz, is completely independent of our problem. Yeah? We always take the same circuit. Yeah? It's a circuit which has a lot of parameters and can therefore reach any point in this high-dimensional space. And we pass in this ansatz into our variational quantum eigensolver. We pass in the Hamiltonian into our eigensolver. We pass in the engine and the initial parameters, and then we let the variational quantum eigensolver run. And this is the number of qubits. Our Hamiltonian knows how many qubits we use. And here you can see I'm using the GPU-based simulator because it's 3 times faster than the CPU-based simulator. And then we watch how this variational algorithm tries to find the solution. And here you see the number of function evaluations, or the circuit evaluations, and here you see the lowest energy that we found. So the lowest eigenvalue that we find. And here it seems like it has found a minimum, right? Now it's getting closer to minus 210. And here we are. We found, the optimizer says he found the lowest expectation value at minus 210. If this is a real minimum, this would be an eigenvalue of our Hamiltonian. And these are the parameters for our circuit. With these parameters, I can construct this eigenstate. Now, what I need to do is, I need to feed in these parameters into our circuit, add a measurement, execute the circuit one time. Here it's totally, it doesn't matter if I use a CPU-based or QPU-based or GPU-based simulator. I only execute the circuit one time. I do a measurement, and then I have my solution. Okay, let's run it. This is the exact result that I know, minus 96. This is the result our optimizer has found. And this is the solution. And the solution says, starting with city 0 at position 0, then at position 1, we have city number 1. At position 2, we have city number 2. And at position 3, we have city number 3. Now let's get back to our problem. So what it says is, start here, go there, go there, go there, and go there. It has found exactly this solution because I added a constraint which says, start with city 0 at position 0 and continue with city 1 at position 1. So I have already fixed the first part. If I would remove these constraints, was this one, if I would put this to 0, then any solution is valid. Yeah, we can start with city 0 at position 0, or we can start with city 1 at position 3, whatever, and then go around in the circle. Okay. So, and here I gave you some samples. What kind of optimizers you can try if you want. I use this one. And I also added some code here. Here, I try all optimizers, and each optimizer I try 10 times. I wanted to give you an impression. How good are the different optimizers? Of course, this takes some time. It took like 4 hours to compute that. And the result is the following. If I don't specify an optimizer, it takes the default one. And here you see the results. Minus 96 is the exact result. So this optimizer from 10 runs finds 1, 2, 3 times the best result, the optimal result. And I also added the times per run. So this optimizer takes 100 seconds per run. This takes 82 seconds per run. This takes 35 seconds per run. This takes 250 to 850 seconds per run. This takes 600 to 1000 seconds per run. And you can also see how good the results are. GNC, for example, it does not find the exact solution. It doesn't find it anyway. Nelda Mead finds it 1, 2, 3, 4 times, but it takes a lot of time. SLSQP finds 1, 2, 3 times, but it's very fast. Powell found the correct solution 1, 2, 3, 4, 5 times, and it's also very fast. So Powell would be the best optimizer in that case. Okay, it's 7:30. Please give me 5 more minutes. It might be interesting for you. Because what I did, I computed this with a simulator and I implemented that with a QUBO for a circuit-based quantum algorithm. We did the same implementation for D-Wave. You might know that D-Wave is a quantum processor which handles up to 5,000 qubits already, but it's not a universal quantum computer. It can only do adiabatic quantum computing, and adiabatic quantum computing is very similar to QUBOs. So we can use exactly the same matrix which we did above. We can send this matrix to a D-Wave machine. D-Wave also has a simulator. And you see, the D-Wave machine gives us the same result. This is the energy. From 100 tries, 93 times, it finds the best solution. And this is the solution. Start at city 0 at position 0 in the path. Take city number 1 on the second position in the path, city number 2 on the third position in the path, city number 3 on the fourth position in the path. This is exactly the same solution with exactly the same eigenvalue. And if we don't run it in a simulator of D-Wave, if we run it in a physical QPO on D-Wave, you see it still finds the correct solution, but we get more errors, more noise. Okay. Yeah, so that's it. I apologize for the hurry at the end, but it's a complex topic. And yeah, and we wanted to give an overview and we wanted also to repeat some of the basics, but we wanted also to come to this point. I hope you enjoyed it. And if we have questions, I'm happy to answer them now.
Yeah, thank you, Marcus, a lot for the presentation. So there is one question which came back several times that what was the largest problems that we were able to solve, the largest CSP problems that we were able to solve? I think that we can separate this question on two parts. So on D-Wave, quantum annealer, and on D-Wave simulator.
Yeah, okay. So with a very naive approach we used here, by using a quadratic number of qubits, compared to the number of parameters that we have. So we have 4 cities, but we need 16 parameters. If we would have 10 cities, we would need 100 qubits. With this naive approach, we could not go very far. With a simulator, we can go up to 5, maybe 6 cities, and then it's done. If we're passing that problem to the real D-Wave QPU, we can probably go up to 30, problem of 30 cities, maybe. 30.
Yeah, because when you go on for the first thing, you need to square the number of the number of the cities in order to get the number of binary variables in your problem. But in D-Wave, you also have this this embedding overhead in the number of physical qubits that you use compared to the number of logical variables in your problem, which is related to the fact that not every qubit is connected in the D-Wave hardware. So, and it's another quadratic multiplication. So you basically go you get the power of 2 of the initial number of your variables. It's a rough estimation. So the number, the size of the TSP that you can solve in a D-Wave is a number of qubits that are available on D-Wave, taking the root, the fourth root. Yeah. 2 square roots.
But now comes the but. You can find better encodings. Here we use a very naive encoding and say we have a binary variable for x for each index, for each combination of index I and j, which gives us this quadratic number of binary variables, and we map that to 1-to-1 to the qubits. We have better ways of encoding that. We have ways of encoding more than 1 parameter in a qubit. And then we come to a logarithmic number of qubits. And then we have solved optimization problems of this kind, of the traveling salesman problem, with more than 10,000 parameters. On D-Wave systems. So, as I said, this approach here is very naive. There's not too much intelligence in how to encode the binary variables into a qubit. We just use 1 qubit per 1 binary variable, but there are better ways, more intelligent ways to do it. And so we can reduce the number of qubits that we need by a logarithmic scale. So if we have 100 cities, we would need 10,000 variables. Then we could use 12 or 13 qubits, something like that. I hope this answers the question.
Yes, I think it answers the question. So there is just people asking for a paper for logarithmic encoding. So if you have something to show us.
No, this is, unfortunately, this is our secret. How to do that, this is our know-how. This is what we use for our customers to implement problems like this. So we have published papers that show that there is a big advantage, but we do not share the internal implementation details.
Okay, so I think that we are We are good now, yeah. Okay, thank you very much for attending the session. So thank you very much, Markus, for the presentation. And maybe like one last question, if someone want to go. Yeah, so I guess WOMANIUM going to forward you the materials, so the slides and the notebooks. I don't know if it was planned, but I guess it was. So
yeah, we will share the slides. I'm not sure if it makes sense to share the notebooks because you cannot execute them, but of course you can look into it and you could implement the same with another SDK.
yeah, I think that was
if
the
there
point.
is a wish, I would also share the notebook, let's say in a PDF format or something like that.
Yeah, I think that that makes sense. Yeah, because you have some interesting information in it.
So I will send the information tomorrow to the organizers of this event, and they can share the information then with all the participants which are interested.
Fantastic. And the PDFs of the slides are already online on Canvas, so you can look right after we conclude the session.
Okay. Is it okay if I do the sharing tomorrow, because I need to prepare a little bit, and I'm in Germany, it's already late here.
Of course.
Okay, great, thank you.
Wonderful. Over to
Okay, then, Marlo, over to you. Thank you for the opportunity to speak here and to share our experiences and our ideas.
Thanks a lot, Markus. Thanks a lot, Margarita. It was a great session. All the participants are really enthusiastic in the Discord as well. And we are hearing a lot of praise for both of you guys. So yeah, a great job. Thanks for being here. Thanks for the session. The participants will be waiting eagerly for the notebooks, maybe in the PDF form. And we will be selecting maybe around 10 candidates to get access for the SDK as well.
Great.
So yeah,
thank you.
Thank you.
Thank you for the fantastic session and for the wonderful collaboration. Everyone, we will briefly bring up the slide, what we will do tomorrow.